Oh, there's so many yummy vegetarian options out there. You could try like lentil soup, veggie burgers, tofu stir fry. The possibilities are endless.
Prepared and compiled by Dr. Nima Madian.
All right, welcome class. As your professor, I am absolutely delighted to have you here for what I really consider one of the most vital explainer lectures in your entire control engineering journey. Today, we're crossing the bridge from the pristine, perfect world of theoretical mathematics into the messy, constrained reality of physical engineering. Let's take a quick look at the syllabus for today. First, linear theory versus reality. Second, diagnosing integrator windup. Third, the anti-windup mechanism. Fourth, tuning the tracking time constant. And finally, digital microprocessor implementation. Let's jump right in. Section 1, linear theory versus reality. This is where the rubber meets the road. Our core objective today is actually quite simple. You need to understand exactly how to bridge linear theory and nonlinear physical realities. You see, in our mathematical equations, a controller can effortlessly ask for an infinite amount of voltage or an infinite amount of valve rotation. But in the physical lab, well, that's just not going to happen. In linear theory, a theoretical PID controller just assumes it has an infinite actuator range, mapping input to output as this beautiful straight line stretching off into infinity. But in reality, an electric motor has a strict maximum speed saturation limit. An electronic amplifier is eventually going to hit its maximum current saturation. A control valve physically hits a travel limit. The internal spool can literally only move so far. So the crucial point here is this. When an actuator heats its physical limit, the feedback loop is effectively broken. The control command keeps increasing, but the actual output simply cannot exceed that hard saturation ceiling. Section 2, diagnosing integrator windup. Let's look at the symptoms of this broken loop. Based strictly on the verified curves we see here, there are 3 distinct phases of failure. First, the saturation event. This is where the commanded control signal U rapidly exceeds the physical limit U max. Second, output clipping. The actual output, U out, is physically constrained at U max, forming that flat plateau you see highlighted. And third, the real danger, delayed recovery. Even after our measurement Y finally crosses the set point, YSP, the commanded signal U remains trapped way up there above U max for a sustained period. The system doesn't respond dynamically at all. It is completely stuck. So what's happening mathematically? During a large set point change, the error remains high. The proportional term does its job and quickly drives the actuator to saturation, shown by U max. But because the error persists, the internal integral term, that dashed purple line you see climbing up, continues to sum mathematically. It is completely oblivious to the physical ceiling of the system. This unbounded internal mathematical growth, this is exactly what we define as integrator windup. The math is running away while the hardware is maxed out. Now, comparing the closed-loop system response curve by curve, the solid line is your standard PID, and the dotted line is the system with an anti-windup mechanism. Let's look at the output Y. The standard PID gives us this chaotic, massive oscillation away from the set point. Moving to the middle graph, the control signal U, we see the solid line stays saturated as a rigid block wave for long periods. Finally, the bottom graph, the integral I. The standard PID's integral swings wildly out of control. But notice the dotted line? The anti-windup scheme beautifully constrains the integral, bringing the entire system into a smooth, highly controlled dynamic response. To ensure absolute clarity, let's explicitly contrast these. For integral behavior, the standard PID grows wildly beyond limits, creating massive peaks, whereas the anti-windup is capped precisely when saturated, flatlining safely. For the control signal, the standard PID lags severely behind error changes, creating those rigid square on-off waves. The anti-windup, however, exits saturation immediately when the error reverses. And finally, for system output, the standard PID results in massive overshoot and prolonged oscillation. The anti-windup gives us smooth settling. The profound diagnostic insight here is that by observing the bottom graph, we see how the algorithm physically clips the integral curve, which directly eliminates that destructive on-off volatility in the output. Section 3, the anti-windup mechanism. Let's decode the architecture of the cure. Okay, systematically walk with me through every single block here. On the far left, we have our error input E, which feeds into 3 parallel PID branches: derivative at the top, proportional in the middle, and integral at the bottom. These branches sum together at the main junction and feed into our actuator block, yielding our rightmost output U. But here is the architectural genius of the setup, the feedback extraction loop at the bottom right. We take the intended input going into the actuator, and we subtract the saturated actual output U.
This comparison yields a tracking signal, A of t. This signal is the exact mathematical measure of how far into physical saturation our system currently is.
Logically, we can break this mechanism down into 4 explicit steps. Step 1 is error calculation. The system compares the intended actuator input versus the saturated actual output, yielding our difference, A of t. Step 2 is feedback scaling. We take that signal A of t and pass it through the 1/TT scaling block. Step 3 is integrator modification. This scaled signal is actively subtracted at the junction from the proportional integral path, right before the pure integrator block, the 1/s. And finally, step 4 is the result. This actively reduces the input to the integrator during saturation, physically preventing the windup from ever accumulating in the first place. Section 4, Tuning Tracking Time Constant. How do we actually calibrate this reset speed? Here is our governing mathematical formulation. TT equals the square root of TI times TD. TT is the tracking time constant, which represents our reset speed. TI is the integral time constant, and TD is the derivative time constant. This beautifully simple equation dictates exactly how fast our feedback loop will react to a saturation event. As a standard practice, we calculate TD dynamically as the geometric mean between the integral and derivative time constants. Additional explanation, why do we use this specific geometric mean as our industry standard rule of thumb? Well, in real-world engineering, we need a balance. If TD is too large, the reset is too slow and windup still occurs. If TD is too small, the reset is too aggressive and you might get spurious, jittery responses to momentary sensor noise. Calculating TD as the geometric mean places our tracking time constant in the perfect dynamic sweet spot, right between the slow integral action and the fast derivative action. Looking at this plot of system output y of t against time, the bold arrow indicates decreasing t. When t is reduced, our tracking mechanism becomes faster. The feedback loop reacts much more aggressively to saturation. Notice how the curves with a smaller t rapidly zero out the integral term. This drastically reduces the system overshoot and significantly shortens the overall settling time. The system just snaps cleanly to the target line. Let's perform a strict verification audit from the controller's perspective. Our y-axis maps the control effort, U of t, scaled from -0.5 to 1. Our x-axis is explicitly labeled time in seconds from 0 to 10. The solid curve represents extreme, poorly tuned control effort. Notice how it drops violently from 1 down to below -0.4 before wildly oscillating. Now contrast that with the dashed curve. It represents a highly constrained, disciplined control effort. It rarely drops below 0 after the initial peak, indicating a much less aggressive, far more stable corrective action by the actuator. Section 5, Digital Microprocessor Implementation. Taking this from theory to real code. And this brings us to the ultimate reality of modern engineering. In today's systems, that entire complex mathematical architecture we just analyzed becomes a simple digital subroutine inside this microprocessor unit. At every single clock cycle, the software numerically calculates V, the intended output. It compares V to the hard-coded actuator limit U, and instantly on that very same clock cycle, it applies the feedback reduction if V does not equal U. It's elegant, it's instantaneous, and it runs flawlessly. Which leaves us with this final, profound question for today's explainer lecture. Is anti-windup just an optional feature? The truth is, in industrial practice, proportional integral control without explicit anti-windup code is completely unusable. It is absolutely not an optional feature. It is the fundamental digital bridge that literally saves our theoretical mathematics from catastrophic physical failure. Thank you for your rigorous attention today, class. Review your tracking time constant derivations, keep questioning the math, and I will see you in our next session.